Rational functions. A rational function is any function which can be defined by a rational fraction, where the numerator and denominator are polynomial expressions. Here are some examples of rational functions. The one that should look most familiar to you would be our parent graph for hyperbola from Algebra 2. That will be the one that we focus on the most for our discussion. Just a key note here, if you didn't remember, that anything that makes the denominator equal to 0 will yield a vertical asymptote on the graph. That's going to be important as we move forward here. First, let's review graphing one of these functions from Algebra 2. A couple things. First of all, if you remember the parent graph and what it looks like, y equals 1 over x, then we can simply shift that parent graph. So remember, it has a VA at 0 and an HA at 0. Now, the reasons behind that we'll talk about here. The reason why we have the vertical asymptote, at x equals 0 is that x cannot equal 0. All right, because we cannot divide by 0. 1 divided by 0 is an undefined answer. Also, any number, it doesn't matter what number you choose, but you can never divide 1 by a number to equal 0. That's impossible. Okay, now we can divide 1 by 1,000,000, and it's going to get so close to 0 that you don't really know the difference between the number and 0 itself, but it never actually equals 0. If you would use your calculator to explore this, eventually your calculator will round it to 0. All right. However, doesn't matter how big this number gets, it'll never equal 0. That's a concept there that we're going to have to come to terms with. Now, how do we go about graphing this? Well, first we identify the asymptotes, and to do that, the horizontal or vertical asymptote is always going to be whatever makes the denominator equal to 0. So in this particular case, 4 would make the denominator 0. So we draw a VA at 4. Okay. If you memorize your transformations from Algebra 2, the plus 3 would be a vertical shift of up 3. All right. Now again, the reason why that vertical shift is up 3 is because this fraction can never equal 0. So that means the only way to get 3 would be 3 plus 0. All right. Well, if this fraction can't ever be 0, then that means you'll never get 3. That's why we have the horizontal asymptote. And finally, we're just going to sketch our graph. All right, we're not gonna do much more than that. I don't need you to go to the table and plot points. All right, I'm looking for the dashed lines at your asymptotes, and I'm looking for a good sketch of your curve. Second example. Let's graph this function. But wait, this is not a function that we dealt with. Now we could determine what the vertical asymptote is by letting our denominator equal 0. So we know that it's going to have a VA at 2, but beyond that, we're kind of stuck right now. Good for us that there is a way to do this. So let's rewrite this function in graphing form. How are you going to do that? All right, I'm going to walk you through it first, and then we'll go over what the steps were to recap. So I have 3x minus 5 divided by x minus 2. The first step, step 1, is always going to be to write your denominator, x minus 2 in this case, into the numerator. Just write it there. Step 2, multiply that binomial so that we can obtain our lead coefficient 3x. So I'm going to multiply by 3 because 3 times x is 3x. However, in doing that, I have some collateral here, and that is 3 times negative 2 gives me negative 6. But my original function doesn't have a negative 6, it has a negative 5. So I need to then add or subtract to maintain equality. Okay, so let's think about this. All right, so my step 2 here is going to say 3x minus 6. I don't want that, right? I want 3x minus 5. So I'm going to have to add a 1 to maintain equality. All right, so let's recap. Let's see what we have. All right, in my third step, I have 3 times x minus 2. And then I have to add 1, remember, to maintain equality if I would distribute. Divided by x minus 2. That the denominator never went away. All right, last step is to split this up into 2 fractions. Remember, when we're dividing by x minus 2, it's both of these being divided by x minus 2. So I end up with 3x minus 2 divided by x minus 2 and plus 1 divided by x minus 2. Cancel when possible. In this particular case, the x minus 2's cancel out. And I'm left with 3 plus 1 over x minus, whoops, 1 over x minus, okay, that's nice. X minus 2. Now this is graphing form. I can observe my right shift of 2, which I already knew about that one, for my VA. And I can observe my upshift of 3 for my HA. This allows me to graph. So we then found out that I was going to be upshift of 3. And just want to verify that it was a positive plus. Okay, so that means first and third. And there's your graph. All right, now if we want to rehash the steps here, I wrote them out for you. All right, to do that, you might want to copy those down. And we're going to move on to the final example. All right, here we go. We're going to do this one. So this isn't changing. And again, the first step is to write that denominator into the numerator. Second step, what do I need to multiply by to obtain this lead coefficient 2x? Well, in this case, it's pretty easy. It's 2. When I do that, I'm going to get the 2x I want here, but I'm also going to get a 4. I don't want a 4. I want a 5. All right. So to get 5, I would have to add a 1 to whatever I did there. Step 3 will be to split this up. So I'll end up with 2x plus 2 over x plus 2 and a plus 1 over x plus 2. My x plus 2's cancel out. And I'm left with 2 vertical shift plus 1 over x plus 2. So I go back to graphing this. All right, negative 2 would make the denominator equal to 0. This fraction will never equal 0, therefore my graph can never equal 2. It's still positive, so I sketch my curve. Now obviously there are much more difficult rational functions that we're not going to necessarily discuss, but these are the area of our focus.